toward the end, I think. Yeah. So what does it say about these things? Let's just kind of read of course, we're going to do more. The book talks about these devices, but then they don't show us how to actually use them in circuit. Well, they tell them how they're hooked in circuits. What page? So it says Zener diodes is a semiconductor device used as what? Voltage regulator. Zener diode looks similar to a silicon diode. So if you hold one of these suckers in your hand, they look just like a diode. So you identify the cathode by the mark, or it's going to have a symbol on the side if it's big enough, right? It says its purpose is to act as a voltage regulator either by itself or in conjunction with other semiconductor devices. So it means if I looked inside a 7805 and I looked at the actual schematic, it's going to have Zeners in there. If I looked on any of these voltage regulators, they're going to have Zeners in there. So what we do is we use a Zener as the reference, and then we have other devices or solid-state devices that we use to actually get the big currents and all that other kind of stuff. Or we can use Zeners by themselves. Everybody okay? A voltage regulator is an electronic circuit that maintains a relatively constant. It don't say constant because there's no such thing as a perfect regulator. Do y'all understand that? But it's going to regulate within a certain parameter. And if it stays within that parameter, we say, okay, it's okay. If it gets out of that parameter, it means that something's going on. Over a wide range of operating situations. Then they show us the what? So this is what we call a VI characteristic curve. And what the VI characteristic curve shows us is how this thing operates. So it's current relative to voltage. So voltage is over here. We got two voltages, and y'all developed this thing for a silicon diode, right? For the 1N914. And but this is voltage here, and then this is current. This is the forward bias, what we see what goes on forward bias. And then this is what we call reverse bias. Now normally a rectifier diode, we want to operate it somewhere in between here, right? So on a regular rectifier diode, we never, ever, 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 ever want it to break over. If it breaks over, we're going to push current through it. It's dropping a voltage. It's going to produce a lot of power real fast, and it's going to burn up. So rectifier diodes and small signal diodes, we never want to exceed the breakover level. We did it on purpose, but we protected that thing with a 10 mega ohm resistor, right? So we broke it over on purpose. Now this is what we call the reverse breakover region right in here. And if we exceed the breakover voltage, then the thing's going to conduct. But you see something interesting when it starts conducting. It avalanches. Right? But if we look at the voltage at its breakover, it stays fairly constant. So what we do with a Zener diode, this is the symbol. So it's got the basic symbol as a diode, but it's got these little angle tips on the end. If you see this, it means this is Zener diode. Now Zener diodes are designed to operate in the reverse breakover. So these guys go into a circuit reverse bias. And what we're going to do is we're going to use that breakover voltage that it tries to maintain. We're going to use that as a power source. If you run a forward bias, it acts like a diode. I mean, if I was going to run it forward bias, I would use it as a diode. I mean, I'd use a diode. Because these guys here have pretty low breakover voltages. We'll look and see. We'll look at the charts. We're going to play around with the 4700 series, the 1N4700. I don't remember I can't remember the maximum these guys break over at, depending on which one you have. So if you operate it below its breakover voltage, it acts like a wall. It acts like a diode. They cost more than diodes. These guys are doped differently. They like I said, they are designed to handle power in the reverse breakover direction. But we're still going to have to protect them. We'll have to protect them with a resistor. That's what we're going to look at. So to use Zener diodes, we'll have a resistor and a Zener combination. And the resistor is what we call RS for a series resistor. And it's in there to protect the Zener when it breaks over. And then we'll take the output across the Zener. So our output we're going to hook in parallel with the Zener. So whatever voltage that sucker breaks over, your load is going to see that voltage. And it's going to be fairly constant, right? You understand? Just like that 0.7 of a volt is fairly constant, that breakover voltage is going to be fairly constant. Now it's going to change. There's no such thing as a perfect regulator, but it's going to be really, really close, and we'll show you how to set these things up. So this breakover voltage, we no longer call it breakover voltage. We call it DC, and we call it the Zener voltage. So that's what we call it. And we're going to operate this thing reverse bias. By the way, you check it with an ohm meter just like you do a regular diode. You put it on the diode scale. One direction is going to measure about 0.7 of a volt if it's silicone, right? Or you flip it around, it's going to should measure in, because your meter's not going to put enough to exceed the breakover voltage. No, that's not true. I've seen some Zeners that would broke off like a 1 volt, but I've seen it in data sheets, but I've never seen them used. So when this thing here breaks over, if we protect it, so if I come over here and put a resistor right here, and then I come over here and put a Zener right here, and then we'll come over and connect this to common. And I'm going to put a plus voltage right there, because that would reverse bias, right? You understand? And then we get up to a certain voltage, this thing's going to break over, and then it's going to maintain a fairly constant output. So if I come over here and put my load right there, it's going to be in parallel with the Zener. So whatever's the voltage drop across the Zener is going to be the voltage drop across the wall, across the load. Y'all understand that? Pretty neat. Now we're sizing that resistor is critical. Y'all understand that? If I use one too big, we're not going to be able to get enough current through it. If I use one too small, you're going to burn up your Zener. And it's not. I mean, if we understand Ohm's law, all you need to do to calculate a Zener circuit is you need to understand Ohm's law. R is equal to what? R is equal to VRI, right? I understand that from the two types of reverse. We have avalanche, which is bad and then we have what we call Zener, and this is what we're going to use. Zener breakdown occurs, or breakover, I guess I should say, at a lower reverse voltage. These guys are trying to break over 5 volts, 12 volts, 10 volts, and that's what we're going to use. We're going to use that Zener voltage. Zeners have a very narrow depletion region. As the reverse bias voltage increases, the reverse current remains very small until it reaches what we call the knee of the curve. See, y'all understand what we call the knee? Well, this right here, we call it the what? Yeah, this is called the knee. Why? It looks like a knee. Okay. Now, to make this thing regulate, we need to operate it at more current. Well, we call it above the knee, which when we talk about, we need to operate it at a current above the knee. If it gets down to the knee, then that voltage is going to change, right, a lot, what we do. Breakover effect begins at the knee. At this point, the current increases rapidly. The breakdown voltage remains essentially constant. Now, it is going to vary with current, just like your forward voltage drop varied with current, but it's not going to vary much, right? You understand? The breakdown, the Zener diode keeps an almost constant current across the terminals within a certain current range. So what would you think IZK would stand for? current flowing through the Zener at the knee. And what would you think IZM would stand for? Well, sort of max. That's the maximum current. These guys are dropping a voltage. We're going to push current flow through them. If they drop a current, if they drop a voltage and we put a current flow through them, we got P is equal to what? V times I. So it means they produce heat. So if we exceed that maximum current, that means we're going to exceed the wattage rating of the Zeners. So Zeners are rated in watts. They're rated in basically two things. They're rated in watts and they're rated in voltage. So when you bring up a data sheet, the two things you're going to see is VZ and power. Now there's a lot more to it because we don't get watts unless we get watt current. So we're doing a 4700 series. These are 1 watt Zeners. Their voltage varies depending on the number, the model number that we go ahead with. Oh yeah, you can, I mean, Ohm's law. Well, here we have to use Watt's law because here we're dealing with power. So we're going to use two laws on this. We're going to use Watt's laws. But what's neat is, is now we're going to come up, and what's neat about a Zener, we'll talk about that. A Zener is a dynamic device. So what a Zener does is it automatically varies its opposition. It varies its resistance dynamically. So back in DC, you dealt with you dealt with circuits that nothing changed. But these guys right here, when we start talking about solid state, we're going to apply every formula that you learned in DC. Just about every formula in electronics is a DC formula. Okay, or an AC formula. Take AC. So those two technologies, you basically got almost every formula that you need for solid state if you're not an engineer, if you're a technician, right? You understand. All you got to do is learn how to apply it. What V and what I, right? What P and what V and what I, what opposition and that kind of stuff. If you can apply that, then you can understand these formulas because they look hairy, but they're not because all they are what? All they are is Ohm's law or Watt's law. But we got to deal with power on this. But this Zener, it's actually varying its opposition to maintain a constant output. I mean, so if the current in the Zener goes up, the voltage is not going to change hardly any. So if the voltage don't change, then what had to change? Well, the resistance had to go down, right? You understand? If the voltage goes up, if the voltage goes down, the Zener current goes down, if the current goes down, the Zener drops the same voltage. Well, if the Zener drops the same voltage at a different current, at a lower current, it means its opposition had to go up, right? So it's varying that dynamic, which is really, really neat. So here's our measurements, right? Here's IZ, we call this Zener voltage. We call this IZT. And this is called the test current. The Zener test current is the current flow through the Zener where VZ is established. So when we say it's a 5-volt Zener, that's usually at test current because that's about in the center of the curve. IZK, which is the knee current, this is as soon as it comes out of the knee. As soon as it's out of the knee, it's regulating, right? And then this is IZ max. If we exceed IZ max, what's probably going to happen? Then it's going to burn up because we exceeded the wattage rating, right? This is given in the data sheets. This is given in the data sheets. This right here is calculated, but it's not hard to calculate. So they never give you IZ max. But they give you the power and they give you the voltage. So we can calculate the watt. Huh? I is equal to what? Using power. I is equal to P over V. So I can take a 1 watt Zener, 5 volt 1 watt Zener. Then I can take what? 1 divided by 5, and that would give me the maximum current I should ever let go through that. IZK to regulate a Zener must always operate above this current. A lot of people get confused because when you look at the diagram, you know, you say this is down, but this is current going up, right? So when we say we need to operate it above the knee, we're talking about more current than IZK. So we have to operate the Z. Let's see. So what do we say? Let's always operate above IZK. IZT is the current flow through where VZ is established. The circuit should be designed to regulate as close to this current as possible. In IZM, this is operating above this current will damage the Zener. The current is not given in data sheets, but is calculated by I is equal to P over V. We've used that formula a few times, right? So there's the power formula. Zener is basically, it's not a voltage source, but we're going to treat it like the voltage source. We've got to have unregulated DC. We're going to bring that into a Zener circuit, but our loads are going to be connected in parallel with the Zener. They're not going to be connected in parallel with the source anymore. They're going to be connected in parallel with the Zener. So whatever voltage is being, and what's the same in a parallel circuit? Huh? No, in a parallel circuit. Voltage. So if the Zener's dropping 5 volts and we put a resistor across it, it's going to drop what? 5 volts. So basically the Zener becomes the source of the current for the rest of the things in the circuit. The Zener impedance can be calculated, a practical. So we have what we call ideal, and this is what we're going to use. So we're kind of using what we call the first approximation. When we do our design, we're going to consider that Zener voltage is perfect. But y'all understand it's not. It's actually going to move at a what? At a slope. But for design purposes and what we need, this guy here is going to be fine. Because what we're going to do when we choose that resistor, we're going to make sure it handles everything. And it's not hard to do. Well, in my opinion, it's not hard to do. But if I use what we call the practical model, which would be this guy right here, then look what all we have to take in consideration. We have to take in consideration the impedance of the Zener. And we have to calculate that by using, y'all know what that means right there? That's the Greek symbol for delta. If you run that in electronics, you know what they're telling you? Huh? It's a change in voltage. So it's a range of a change in voltage and how much range did that current change. And you'll see this used a lot in devices that are dynamic or things that's changing. So to calculate the practical model, we'd have to calculate the Zener impedance. And of course we would have to, and we'd have to know Z is specified on the data sheet. So the Zener test current, when we look at the data sheet current, what they do is they give you this current, they give you this current, and what do you have to do with this guy? You have to solve for it. That makes sense? Are we okay so far? So we're going to use ideal. In ideal, the Zener acts like this. Now, but it's not a voltage source. The source is coming from your regulated power, from your unregulated DC, right? So this is what we're talking about. Characteristic curve, the slope is exaggerated in this illustration. It's not that bad. This is the way we calculate the Zener impedance. And it's given, by the way. So the data sheet, it gives us the Zener impedance. If we wanted to get really tight, it gives us the temperature it's designed to operate at. It gives us the power dissipation. Now electronics, anybody know what die rate means? Take a guess. That's a term you should know. Huh? Die rate. So you die rate something. What do you think that means? Huh? What? Decrease. So when we die rate something, we decrease it by a certain amount. So they'll give us what we call a die rating factor. What they do on the Zener is basically deals with temperature and the length of the leads. And we'll see that. Zener voltage, Zener test current, we're going to need that. We're going to need the knee current. We're going to need, we didn't put the knee current. Zener voltage, we call that what? It's called VZ, all right? And then what we call IZ max, and we're going to have to do what with IZ max? We have to calculate. So let's go back and, let's look up the 4000 series. This is, I got mine up here. Y'all can look it up on the data sheet on Blackboard. And I might need to bring it up on Blackboard. Can y'all see mine? Or is that just too small? Huh? Yeah, I think it is too. Y'all go ahead and take a 10-minute break. Let me pause this. So this is the data sheet for the 4700 series. You know, the very first page where they show us. They show us these are what? 1 watt. So we got different models, 3.3 up to 100 volts, right? This says our power rating on it is 1 watt, and it says we need to dirate it by what 6.67 milliwatts for every degree centigrade above 50. Does that make sense? Okay. This tells us we should dirate it depending on the length of the leads. So the shorter the leads, we get more toward 1 watt. The longer the leads, we get away from 1 watt, right? That makes sense. We talked about that. Of course, we're not going to have to worry about that stuff. This is what we're looking at right here. So these are all the 4700 series of Zeners. This is a JEDEC registered part, so that means there's a ton of people that makes the 40. JEDEC is the Joint Engineering Council of Electronic Devices. This is kind of an organization where people can register the mechanical part of the device. We call them packages. So what's nice, if they register this package, then that means it's open technology so anybody can use it, but then it means your device would get more support because there's more support for that package. Does that make sense? So I think this is JEDEC registered, and I think there's a handout up there that's got the JEDEC packages on there. This is a DO7. This is a DO7 package. And it's open technology, so I mean you're going to see tons of people use this thing to make any 2-terminal device. So what's this over on the left-hand column? And that's part number, right? That we'd buy. And then the next one is a very important column. What's this? That's our Zener voltage. And it's given at IZT, right? Y'all know what IZT is. That's that test current that's in the center. This is the test current right here. So that's where this is where this is established. These two right here, we're not going to use these right here. This gives us the actual Zener impedance. We are going to use IZK. So here's IZK. And what else do we need? And that's about all. This is the surge current. So this guy here could, if we surge for maximum surge current for, I can't see the milliamps, but it's got a note down there. This guy, surge current on this thing could actually go up to 1.3 amps. But that wouldn't be for very long, right? So we're not going to use this. We are going to use, this gives us the leakage current, which is no concern for us right now. We are concerned with IZK. That's the knee current because we gotta regulate above IZK, right? And we gotta regulate below IZ max. And that's about what we need. IZ max we're going to calculate by power. Everybody okay? This says these guys, so it's JDEC registered, Joint Electronic Device Engineering Council. See note 1. Tolerances and type numbers. These JDEC type numbers listed above are standard. So if I buy a 1N 4763, it's rated at 91 volts, which would give us a tolerance of plus or minus 10%. Now, if it's a 14763A, then it has a tolerance of what? Did y'all bring it up on Blackboard, or are y'all looking at it? I'm looking at note 1. I can read it on mine, so I'm sure y'all can read it on yours. Tolerances and type number designation. The JDEC type number listed have a standard tolerance of a nominal Zener voltage plus or minus 10%. A standard tolerance of plus or minus 5% on individual units is also available and is indicated by suffixing a what? A. So that means if we get a 1N 4763, that would be plus or minus 10%. A 1N 4763A would be plus or minus 5%. That makes sense? Yes or no? Yeah, we got some of these. Let me pause this and go. 35 is a 6.2 volt Zener, 1 watt Zener. This is a 4744. So 4744 would be a 16 volt Zener, or 15 volt Zener. 4742, what would that be? 12 volt Zener. Are you okay? And they look just like diodes. I mean, we can get them down to, these are a little bigger because they're bigger diodes. You know, you can't tell them. This is a 1N. This is not a 47. This is a 1N 50s. We'd have to look this up on a different data sheet. But that's a Zener diode too. That looks just like the 914 that y'all been playing around with, right? These are 1N 4733s. What's 1N 4733? These are 5.1 volts. So once we figure out so all we do is we figure out, okay, what do I want to regulate at? Now you're going to have to regulate at a standard voltage, right? You understand that? We find the voltage down this column right here, and then we would design our circuit around this. The only thing we're really going to need to design is we need to know the load required. We need to know the voltage required by the load, right? You understand that? And we need to know the current required by the load, which that would be on any power supply. We need to know IZK. We need to know IZ max. And after that, we're pretty much ready to design the thing. Using what laws? Ohm's law. And Watt's law. We got to use Watt's law just to make sure we're not going to burn it up. So we calculate the size of RS. Then we calculate the Zener power. If it's over what we wanted, then we'd have to go to another Zener. We'd have to find a Zener that does the power that we need the Zener to do, right? Does that make sense? Or redesign or change the load that we're going to work with. What's that? Well, if you hook them in series, then the voltage would be double, right? And they would well, if you did it in parallel, it's not going to any impact, you know. Because they're dynamic devices. When you start dealing with dynamic devices, you're worried about one guy stealing the show. So that happens a lot. Where one guy, if these guys are not exactly the same, the odds are they're not. And we have that problem with looking at transistors in parallel and stuff like that. You would think you'd be okay. You think you'd get twice as much current. You don't, because usually one of them tries to steal the show. And he'll burn up, and it burns up other. But you can do things with transistors. So what I would do is I would just find a Zener that could handle what I needed to handle. Now, Zeners can be the actual voltage regulation for low current applications. If we don't, but what we can do is we can use the Zener voltage as a reference and use it to drive other devices that get higher current levels. Later on, we'll look at bipolar transistors. So I could use the Zener as the reference for the bipolar transistor, and the bipolar transistor could run the load. That makes sense. And that's what just about all your voltage regulators do. So if we look at like a 78, this is a 7800 series, and it's got all these bipolar transistors in here we'll talk about, but sitting right here in the heart of it is what? Zener diodes. So we're using the Zeners for the reference for the 5 volts, or the reference for the 12 volts, and then we're adding all this, then we're supporting it with all these other electronic devices, not only to decrease the current, but also add current limiting and over voltage and all the other kind of stuff. There's a lot more to this. This is actually a print on a 200 watt ATX power supply. And it looks complicated, but after a while you learn this stuff. But over here on this side, right in here, what do we see? Zeners. Down here we see what? Zeners. This is probably the main guy right there. This is a switching power supply too. So, but it gives us 3 out. I mean, it gives us a plus 12, a plus 5, a minus 5, a minus 12, and then a plus 3.3. Notice they only feed back the plus 12, because so here's our feedback for regulation. This is the actual oscillator chip right there. But if the 12 volts is right, and since all these are done by transformer ratios, right? You understand? If the 12 volts is right, then what? All the rest of them have to be right. Does that make sense? So when this power supply, when it checks to see which one's right, it checks the 12 volt supply. If it's right, then all the other volts, they assume all the other volts. Does this scare you? Nah. So what we're saying is it's very simple to build a nice, cheap little regulator, using nothing but a Zener and a resistor and a transistor, or a Zener by itself. We'll see Zeners used all the time to power up, to change the voltage levels. So let's say I got a device that needs to run off 5 volts, but my power supply, everything else in the system is 12 volts. Well, all I have to do is just take that 12 volts and use a 5 volt Zener to power that one device. Does that make sense? So we see this done a lot. We see these guys used in limiting circuits. So if the voltage gives for over voltage protection, so you put them in their reverse bias, and if the voltage is below the limit, it won't break it over. If it gets above the limit, so avalanche and fire something and turn your power supply off so you don't burn stuff up, right? So they're used all over the place. It takes a varying DC unregulated and keeps it relatively constant. But Zeners it's like most electronic devices, they only work over a set range. If you get outside their range, then most people call it their zone of comfort. So as long as you're operating in your zone of comfort, you're okay. When you get out of your zone of comfort, things happen, right? Well, usually in solid state devices, if you get them out of their zone of operation, what's going to happen? They'll probably burn up, or won't operate at all. So this is what we're going to do with a Zener. We're going to have a series pass resistor. We're going to refer to it generically as RS. And then that Zener right there is that the function of that resistor is to drop the difference between the unregulated voltage and the regulated voltage. That's what is in there. And sizing that thing is critical. So what happens is your input voltage changes. So here the input voltage is over here. This guy right here is going to drop a certain amount of voltage. This guy right here, so if the input voltage drops, then the voltage drop across IR. What does Kirchhoff's voltage law say for a series circuit? Huh? What's Kirchhoff's voltage law says for a series circuit? Well, what it actually says, you're right, but if we subtract, but it says the sums of the voltage drops have to equal to the applied voltage. Okay. So let's say this guy right here is dropping 5 volts. And then over here I have 10 volts. So who's dropping the 5 volts? I mean, who's dropping the difference, excuse me, who's dropping the difference between this and this? Huh? The load, we don't even have a load hooked up to this thing right now. Now, that resistor right there. Okay, what determines how much voltage a resistor drops? Huh? Yeah, and so V is equal to what? Okay, I what? Times R. Okay, so let's say over here this thing drops down to 7 volts. This guy right here is still 5 volts. So what's this resistor got to drop now? Okay, it's got to drop 2 volts. Well, up here it's dropping what? 5. Down here it's dropping 2. So what has to be changing in the circuit? I didn't change the size of this resistor. So let's say this is a 1K resistor. Well, now this guy here, to drop 5 volts, it's got to conduct 5 milliamps. But it's 1K. It's 1K. It's not changing, right? You understand? Down here, it's still 1K. Now it's going to conduct 2 milliamps. So what changed the current? What had to change? If the 1K is not changing, right? If the 1K is not changing, then what's changing? What's got to be changing? Huh? But what's making the amps change? I is equal to what? Okay, I is equal to V over R. Well, this R right here is not changing. That R right there is not changing. What's changing? What's changing? This is staying at exactly 5 volts. The voltage drop across the resistor is changing. Okay, you understand. So that means the current flow in the circuit's changing, right? But why is it changing? I mean, why, if this guy here is dropping 5, how can it keep dropping 5 volts if the current's going down? They're in series. So this is in series. So this is my circuit right here. We don't even have a load hooked up to this yet. Undoubtedly, y'all don't understand my question. So we're coming over here. The Zener's dropping what? 5 volts. This guy's dropping 2 volts. Up here, we come over here. The Zener's dropping 5 volts. This guy here is dropping. So the Zener is staying exactly the same voltage, even though we're ranging the current, right? You understand? So that means what's got to be happening. So here we have 2 milliamps of flow. Over here we have 5 milliamps of flow. Right? You understand? But this guy right here is dropping 5 volts. So the current flow through the Zener is changing, but the voltage drop across it is not. So what's going on? So V is equal to I times R. So up here, the current is high, the voltage is the same. Over here, the current goes down, the voltage is the same. So what's got to be changing to make that dang Zener drop 5 volts all the time? Huh? What? The R's got to be changing. So what you're seeing here is you're seeing that dang Zener dynamically change its R depending on, to maintain a what? A constant voltage. So it's not, that R is changing. It's changing all over the place. So if the current tries to go, if the current, I mean, you understand that. So what we're doing is we're letting the Zener current vary but the voltage drop across it doesn't change. Well, it does a little bit. So that Zener is dynamically changing its R to try to maintain a watt. So even though the current's changing, the voltage drop across it's not changing. So what has to be changing? If V is constant and I is changing, then what's got to be changing to make you always come up with the number 5? Y'all understand that? Yes or no? So this is what we're talking about. These guys are amazing to me because they dynamically do what? Change their resistance to try to maintain a. So even though the current's changing, the voltage drop across them is not changing. Well, we say it's not changing because we're thinking about an idea. They're going to change a little bit, right? But as long as we don't let that current get below IZK, and as long as we don't give it above IZM, this guy's going to work. If we get it below IZK, it's going to drop below 5 volts. It's not going to have enough voltage to regulate, right? You understand? And now it's going to vary like crazy. If we get it above IZM, what's it going to do? Good chance it's going to do what? Burn up. Any voltage applied to the Zener that is above the voltage, the knee, will be considered a short circuit. A resistor, so if I let this sucker break over and I did not have that resistor in series with it, the Zener would be gone just like that. A resistor is connected in series with the Zener. We're going to call it what? It's RS. What's the purpose of that guy? Got one person. Yeah, it's going to drop the difference between the what? The unregulated and regulated. Calculating the size of the resistor is critical to the operation of the circuit. If you put a resistor in there that's too small, you're going to burn your Zener up. If you put a resistor in there too big, you'll go below IZK and you'll go out of regulation. Won't hurt the Zener, you just won't regulate it anymore, right? Everybody understand that? What formula we're going to use to calculate R? R is equal to what? V over I. So here's our Zener circuit. So positive unregulated, so this would come from what we used before, right? We would have a what? We would have a transformer, and then we'd have a rectifier, then we'd have a what? Filter, and then we'd have our resistor, and then we'd have our Zener. And we're going to hook our load in parallel with the what? Zener. Not with the resistor, with the Zener. Because the voltage across the resistor is going to be changing, but the voltage across the Zener is going to be fairly constant. And the rule of parallel says voltage in a parallel circuit is the same. So if I set a voltage across the Zener, then everything else out there is going to be the same, right? So this is the basic Zener regulator. I'll hook my load out here in parallel with the what? Zener. Okay, so tell me how we're going to do that VS. What do you think some of the things, not VS, RS, what do you think I need to know? What do I need to know? So R is equal to what? V over I. Now, what's his function in life? To drop the difference between the what? Unregulated and regular. Now, what's wrong with the regulated voltage? It's changing, right? So we need to know the range that it's going to change. So let's say this is 10 volts, and it's going to change. Let's say it could be as high as 11 and as low as 9. Okay, so what size Zener? What's our Zener voltage? Got to have it. It's got to be less than 9, and we want it to be. It's got to be less than 9. We got to have a Zener that's below where our unregulated is changing, right? So what do y'all want to do? Now let's do a 6-volt Zener. Yeah, we're fine. So how much is that resistor going to drop? What's the maximum that resistor should ever drop? According to Kirchhoff's voltage law. Somebody help me. Y'all are experts now. What's the maximum that thing's going to ever drop? Somebody give me an idea. Come on. Kirchhoff's law says the sums of the voltage in a series circuit have to equal to the applied voltage. I'm going to have the maximum I can have over there is 11 volts. My Zener's dropping 6. What's left over? Okay, so the maximum voltage VR is going to drop is 5 volts. A lot of people say it's going to drop 11 volts, but remember, we got two things, right? You'll understand that. What would be my VR minimum? The minimum voltage that resistor would have to drop. 3. Good. So now I know a range, right? You understand? Which voltage are we going to use? No, we can't. Can't choose. Got to pick. Well, what we're trying to do is we're trying to operate it a current above the knee, right? You understand? We want to make the current always be above the knee. So when would I get the minimum current in my Zener? When that resistor is dropping 5 volts or when it's dropping 3 volts? Huh? Why is that? Because it's a series circuit. So if my resistor is dropping 3 volts, that means, because if the voltage goes up, the Zener current is going to go up, so it's going to move away from the knee, right? You understand? So what we're going to do is we're going to use the minimum voltage. So I'm going to say R is equal to my minimum voltage. What's my minimum voltage? Okay, 3. Y'all understand what y'all's 3? Because if it goes up to 5, the Zener current is going to go away from the knee. Right? You understand? Okay. Now what we're going to choose for I. Well, we got to know some stuff. We got to know the load that the Zener is going to have to run. So what kind of current load y'all want to run out here? Not a big one, a little one. Let's give it in the milliamps. What y'all want? Huh? Okay, so 10 milliamps. So let's say we're running a 10 milliamp load out. Okay. Now we got to do two things. So here comes my power right here. So here we're going to draw a positive current. Let's don't do negative current. We're not going to run through ground. So here comes my two current paths. So I've got to support my Zener current. If I let my Zener current go below IZK, then we go out of regulation. And I've got to support this guy right here. So that means that resistor is going to have to support 10 milliamps. Plus, I've got to have at least what? What's the minimum current I can keep it through my Zener and let it not go out of regulation? Huh? What's the current? The minimum current I can put through my Zener and not let it go out of regulation. Okay, so what's the minimum current I can put through my Zener and not let it go out of regulation? If I exceed IZ max, it's going to burn it up. Okay, IZK. So I've got to support two currents. My Zener's always got to support two currents. It's got to be above, it's got to be at least IZK, right? You understand? And it's got to support the current of the. Okay, so let's look up a 1N47 series that's a 6 volt Zener. You tell me what IZK is. Okay, so it's got to have 1 milliamp, right? Got to have at least 1 milliamp. Let's redo this. Hold on a second. Let's do it like this first. No. What I'm going to do. Okay, I'm right. So 10 milliamps. So what we're going to do is we're going to use the minimum voltage and the maximum current. What's the maximum current the load's going to have to support? I've got to get this right. And then we're going to add IZK to it. What's IZK? Okay, so we're going to say R would be equal to 3 volts over 11 milliamps. What's that going to give me? Huh? 272? Okay. All right, now the problem we have is there's no such thing as a 272 ohm resistor. Unless we use a pot. Pots cost about $5 or $6 a piece. So what we're going to do is when they make resistors, they make them in standard values. So on Blackboard there is in the handout section, there should be a standard resistor value chart in there. So look it up and tell me what would be our next standard value. First of all, are we going to round up or round down? Okay, if I round up, we're going to go into IZK. So we're never going to round up. We're trying to move away from the knee, right? You understand that? So if I choose a smaller value, we're going to put more Zener current in there. If I choose a bigger value, we're going to move it toward IZK. So we always, even if it falls on a standard value, we always go to the next level. So y'all see it on Blackboard? Y'all got there? Y'all see it? Isn't there a standard resistor chart on there? Okay. Let's use a 5%. Is there a 5% chart on there? So this is the absolute maximum resistor I would use right there. And there's no such thing. So what's our next standard value? 270. What would be below a 270? 240. Are we okay? Yes or no? Everybody okay? So 240. And then I'm going to multiply that times 1.05. What does that come up and give me? Do y'all understand what I did then? Yes or no? Huh? 252. Then this guy, then 240 is going to be fine. What I did is we have to guarantee that this thing never, ever gets above 272 ohms. If he gets above 272 ohms, then we go into the knee and we go out of regulation. So what I just did is I increased this thing by 5, it's a 5% resistor, so I multiplied by 1.05 and that gave me the value. So it came up to be 252 ohms. That's less than that, so this resistor will be okay. What if it came up to be more than that? Then we would go back, we would go down to the what? The next standard value, right? You understand? We're trying to move this thing toward IZK. Away from IZK, toward IZK. Okay, so I'd use a what? 240 ohm resistor. Using Ohm's law. Everybody understand that? Yes or no? Did I lose anybody? So if the load current goes down, Zener current goes up, which is going to be okay. It's going to move it away from IZK. If the load current goes up, then Zener current's going to go down, which is going to move it toward IZK, but we should be okay. Okay, so 240 ohm resistor. Tell me what I need to do next. Is all 240 ohm resistors equal? Okay, what's two things resistors are rated at? All right, so I got to make sure I choose the right wattage resistor, right? So I got to calculate watts. Not for my calculated resistor, for my chosen resistor. What's the maximum voltage it's going to have to drop? 5 volts. So power would be equal to 5 squared over 240 volts. This is why knowing those other power formulas makes it easy. So V squared over R. So when you calculate the power, you don't use the minimum voltage it's going to drop, you use the watt. Maximum, don't that make sense? What's that? So we use quarter watt resistor right there. Quarter watt is 250 milliwatts. That would be fine. That's double, right? So now we not only know what size resistor to stick in there, we also know, make sure we buy the wattage resistor. I think I told you my power supply story, right? Where they burn up all the resistors. Did I tell you that one? Oh, we used to have enough time in the class where we taught a class called power supplies. And what the students did during that class is they designed and built the power supply. And then they had to write the specs on it. Well, what they were supposed to do was to load the thing with a 100 ohm resistor and turn it all the way up. It was like a 30 watt supply. And they'd come up there and they'd say, well, something's wrong with our power supply. It keeps burning up resistors. Well, what was the problem? They was using quarter watt resistors. 30 volts, quarter watts. I forgot what the value, I think it was 100 ohms. So 30 squared over 100 ohms, that greatly exceeds quarter watts. And it was burning them suckers up. So what they were doing is they were looking at the value of the resistor, and they wasn't concerned with the watt rating of the system. So you got to make sure you understand these wattage ratings on these resistors, or you're going to burn a bunch of them up. Or either you're going to choose one that's too big and pay more money. Okay, so what do we need to do now? So we chose our resistor. So what we're going to do is we're going to size a resistor that drops the minimum voltage at the maximum current plus IZK. Does that make sense? Why IZK? Because we don't want to always operate it above IZK, right? So there's V is equal to what? Y'all got the formulas in the sheet, right? So we say that RS is equal to V max, VR max divided by what? Should be I the load maximum plus IZK, if you look at the formula sheet. Okay, so it's formula sheet. So we're looking at Zener diodes. And then what do? We calculate the resistor. Then what's the next thing we did? Somebody tell me. We looked it up on a standard resistor chart, right? What did we always do? What do we always do? Round down, because this guy right here is going to fit it at the knee. We round down, so that moves us away from the knee. Then we did what? Then we calculated the tolerance to make sure that it did come up to be greater than this, greater than or equal to this, or even close to that. And then what do we do? Then that's the resistor we chose. 240 quarter watt resistor would work in this power supply just fine. Now what do we need to do? Let me guess. So why hook this thing up and burn up my Zener? I'm not saying it's going to do it, because I didn't do what? I didn't check to see if this resistor would not let too much current flow through the Zener where it would exceed the 1 watt wave rate. So what do we need to do now? We need to calculate Zener power, worst case. What would be the worst case? Worst case would be if this resistor came undone, and then that guy had to conduct that 10 milliamps at 5 volts. So somebody tell me, so power is equal to what? Main formula. Okay, so what V are we going to use? We're calculating power of the Zener, so we're going to use what? Hopefully we're going to use Zener voltage. And then we're going to multiply that times current, some current. What's the current? Okay, so IRS max, what's that going to be? So that's going to be 5 divided by 240. So now we're going, so IRS max, when's it going to get the max voltage? I'm sorry, when is it going to get the max current? When it's dropping the maximum voltage, right? So it's going to be 5 divided by what? 240. Okay, so what would I through the resistor max be? What's that? Yeah, 20.8 milliamps. And then what will we do? So the formula is it's IR max minus I of the load minimum. Now what we're going to do is we're going to say, okay, what if I remove the load? Well, if I remove the load, then it's got to support this 10 milliamps right here, right? You understand? Plus that Zener current. So in this situation, I would say PZ maximum would be equal to, what's our Zener? 6 times 20.8 milli. So what's the power of that Zener? I'm waiting. Milliwatts, right? Okay, so can I use that 1 watt Zener there? Huh? Could I use that 1 watt Zener there? Oh yeah, it's gonna be sitting there idling, right? You understand? This circuit right here, we could completely unload it, and that Zener would only dissipate 125 milliamps. You got to understand when you remove the load, it's got to conduct that, right? You understand? It's going to regulate. And if we chose the wrong size of RS and we unloaded our power supply, what could happen? We could burn the Zener up. And that's it. So what laws did we use here? So, but what we had to do is figure out what voltage do we want it to drop? What do we want to do? What do we want to do? We want to move it away from the knee, right? That makes sense? So see y'all Thursday. Yes, we do. Oh, really? That was the last time we talked to class. You should have said the first week and second week and third week and. I need my Zeners back out.
When I actually submitted it, said that it was late. March.
Oh, I know what's going on. I'm sorry.
Yeah, it was just.
What happens there was a due date on them. So they're right on the calendar.
Yeah, they're right on the calendar.
And they're just, yeah, thank you. It did let you submit them though, right?
Yeah, it did.
Let me take.
So he gave you 1, so
I'm still short 1. I'm gonna shut this down and do that in my computer in there. It's too hard.